Great. Thank you so much. Well, this is my first chance to be part of this network, so I really appreciate it. And I thought, given that it might be helpful to at least say quickly who I am with a little bit more of an introduction. As I mentioned before, I am an assistant professor at the University of Michigan, which is in the Great Lakes region of the U.S. Previously, I was at the National Center for Atmospheric Research, where I was part of the aviation facility, and taking measurements by plane is something I've become pretty passionate about, as it gives us a chance to actually be in the atmosphere, making measurements on the spot in situ, and having a chance to actually see the processes and the data come in as we're flying through the atmosphere and the moisture in it. But I also have a long history of making measurements in a lot of remote places, whether it's forested sites now in the Great Lakes or mountaintop stations where we get a sense of the larger scale moisture transport. So in general, I'm interested in questions about moisture transport, where moisture comes from, and one of the tools I use, as I'll introduce a little farther down, is isotopes in water. So I wanted to start with this motivating question, which may seem very simple, but I think it's one that resonates with the public at large, and certainly with this group. That question of where does our moisture come from in general, right? We think about this from a community perspective, and as Agnes has nicely shown, because of the importance of crops and their dependence on where moisture comes from. And if you look at water tagging in simulations, so in comprehensive models where we can explicitly tag moisture from a particular spot and then see where it ends up, whether it's in clouds or in rain, what we notice is that less than half of the precipitation in most regions originates locally. And of course, this has a bit of dependence on how we define the regions. And in this particular study, which was done by a colleague and friend of mine, Hansi Singh, you can see that the regions, as outlined by this red box, are actually quite large. But the take home here is that really, in most places, a sizable proportion of our moisture comes from somewhere else. So I'm going to call this remote moisture throughout this talk, and talk about the dependence of our water resources on remote supplies. So another thing that Hansi did in her work was she looked at these doubling CO2 experiments to understand how our dependence on remote moisture would change. And so in this zonal mean plot of precipitation, where you're looking at precipitation in millimeters per day, that's the change in precipitation is given by this blue line, going from the South Pole all the way to the North Pole. And what you notice is that if you break that down into contributions from changes in local moisture, which is the green line, versus remote moisture, the red line, you notice that nearly all of the change in precipitation in a doubling CO2 world is coming from changes in our remote moisture dependence. And this, of course, comes from the tags that I just showed you. So a very sophisticated way of thinking about where our moisture comes from. But you could also do this in the zonal mean with all climate models, right? Because then you can just sort of track where moisture, what zone moisture comes from and what zone it goes to, in order to understand what the transport distance, or we might call that characteristic distance, a length scale, what that moisture length scale is. So a student who had worked very closely with myself and Hansi just finished this paper this year, Kyle Hablom, he had looked across CMIP-6 experiments. And as you can see, he looked at a whole variety of warming experiments, not just increases in CO2, but then also a variety of different warming pathways or business as usual pathways. And what he found is that across models, which are indicated by all these different symbols here, and across experiments, which are given by the different colors, you notice that there's a lot of consistency. All these models show an increase in moisture transport distance on average as we get into a warmer world. And that's associated with this decrease in what he calls the moisture cycling rate. But if you took the inverse of this, this is essentially the atmospheric residence time. So as the atmosphere warms, we see moisture spending more time in the atmosphere. And as it's spending more time in the atmosphere, it's traveling longer distances. And so the implication is that then the moisture that you receive in your location actually has come from farther away. So the question I wanted to address in this talk is, outside of models, is there observational evidence for moisture becoming more remote, coming from farther distances? And the short answer is yes, and it seems to be linked to shifting storm dynamics. So this is where I go into more of the work that we've been doing. And some of you may be familiar with the idea of stable water isotopes. For example, if you had seen the review paper that Luis Comeno and his group had put out, Recent Progress on the Sources of Continental Precipitation, one of the sections in this paper talks about the use of stable water isotopes as a way to provide a fingerprint of the origin of water. So let me tell you a little bit about how we do that. So in a nutshell, isotope ratios of hydrogen and oxygen in water provide this integrated record of evaporation and precipitation. So on the left here, I'm showing a variety of different water molecules. We have what we would consider our isotopically normal or light water, H2O, but then we also have these heavy variants, which either have a heavier oxygen with extra neutrons or a heavier hydrogen, which we call deuterium. And so the isotope ratio by definition is simply the heavy to light concentration. So either the number of DHs or the number of 18Os to 16Os. And since these numbers tend to be very small, we normalize them to a standard. So we look at a relative difference from a geochemical standard and then express that as a delta notation. That's the difference. And so delta D for the hydrogen isotope ratio and delta 18O for the oxygen isotope ratio. Now, I'll tell you a little bit more in a minute how isotope ratios capture evaporation and precipitation, but the important point I want to stress here is that if you understand the patterns of evaporation and precipitation, essentially you also understand something about the moisture transport. And that's because if you look at this from a water balance perspective, you know that differences in precipitation and evaporation have to be balanced by this moisture flux convergence term, which is essentially representing transport. And another way we could think about this is that the convergence is representing the remote moisture and evaporation is representing the local moisture. So to understand a little bit more about how isotope ratios capture these E&P patterns, thus giving us a sense of moisture transport, think about this. The heavier water molecules thermodynamically prefer the condensed state. That means that if you have an ocean body or a large body of water, it's going to have a relatively large supply of these isotopically heavier molecules. When you evaporate from that moisture source, then you end up enriching the atmosphere in the heavier isotopes. That increases your isotope ratio. But then as soon as you condense material, the heavier water preferentially condenses and is actually lost preferentially through precipitation. And that means that isotopically lighter water vapor is left behind. And as you continue to move through a transport path, you continue to lose heavy water preferentially, which means that you progressively lower your isotope ratio. So this is essentially one of the signals we start to look for is these changes in isotope ratio. But maybe one thing you've picked up on in this little schematic that I've shown you is that you're losing both heavier water and you're losing the total mass of water through a condensation process. And so to first order, there's actually this linear dependence of delta D on the log of specific humidity. In other words, as soon as you start to condense out water and reduce the specific humidity of the atmosphere, you also reduce your isotope ratio. So that would be a typical thermodynamic prediction. What we need to look for to understand changes in moisture source is some signal that's independent of the change in moisture quantity. And so we look for this Q independent signal. And actually what we look for specifically is a lowering of the isotope ratio for a given specific humidity or for a fixed specific humidity. That lower delta D for fixed Q has been related or shown to be connected to convection that relies on convergence from more remote sources and also convection as it starts to organize. And of course, more organized, bigger storms tend to pull in moisture from more remote places. So to try to illustrate this, I'm going to give you one example with hopefully a climatological pattern that may be familiar to you, which is the El Nino phase of ENSO. And then we'll move on to showing you what the longer term trend in this is using satellite retrievals of isotope ratios. So how this works in practice, if we look at composite differences between El Nino periods and La Nina periods in the recent past, where we have satellite information of both isotope ratios, and then we can use reanalysis for information about temperature or moisture flux convergence. What we notice, first of all, just looking down here at the bottom plot, during an El Nino phase, we have this warmer temperatures in the Eastern Pacific, as we expect, that warm tongue with El Nino. And then what we see in the isotope ratio record, which is shown here above in the shading, is that there's a close correspondence between these higher isotope ratios with the warmer temperature patterns. And also on top of the shading here, I'm showing temperature in the contours from ERA. So you can see how closely the higher isotope ratios map to the higher temperatures. So this is essentially that first order following of moisture. It gets warmer, the atmosphere gets moister, the isotope ratio increases. Okay, a basic thermodynamic prediction. How do we start to see that the moisture sources are changing between El Niños and La Niñas? To do that, we look at this isotope ratio to fixed humidity. So essentially, we're normalizing the isotope ratio by humidity or looking for that Q-independent signal. And as soon as we do that, we have a very different pattern where you notice these lower isotope ratios at fixed Q in the central Western Pacific. The contours in this case are now the moisture flux convergence and divergence. So convergence is shown by these dash contours. These are places that are getting more remote moisture, pulling it in for convective processes, whereas the solid contours are showing you the divergence. So you can start to see as soon as we look at this more normalized isotope ratio, then what emerges is something that's related to the transport patterns and where the moisture is coming from. So let's take a look at the longer term satellite record. And from AIRS, which is the Atmospheric Infrared Sounder, a NASA sensor, we have data that was continuously processed in the same way 2002 through 2019 or 2020. It turns out that there is data still being collected, but it's being processed a little bit differently since 2020. And so we've chosen just to look at the period with consistent processing. When we look at that essentially 2-decade time frame, what we see is a pattern that actually looks a lot like what I just showed you. It looks a lot like the moisture convergence pattern that we see with El Nino versus La Nina, with these cooler or lower isotope ratio patterns in the central Western Pacific. Now, to be able to remove this ENSO signal and see what's actually a longer term trend in the data, we use empirical orthogonal functions, so an EOF analysis to separate out the ENSO-like patterns. So ENSO is our first mode of major variability. That's shown here. As soon as we look at the second mode of variability, what we see is a pattern like this, where we see isotope ratios tending to decrease, especially over convergent zones like the ITCZ and SPCZ, and also over continental regions, so quite a few of the land masses. So I'm not showing the time series here, but if you looked at the time series of this pattern, what you would see is that it is increasing in time, indicating this tendency for lower isotope ratios at fixed Q. And as I mentioned, that implies it's consistent with greater moisture convergence and a reliance on moisture from remote sources over these regions where you see the blue color. So we see this 2-decade trend, but how can we link this to some sort of mechanism? I mean, one of the things that we have to consider is when we think about these average transport distances or characteristic transport distances, these length scales, no single atmospheric parcel is really following these average pathways. It's an average or composite of many different parcels moving in various directions. And of course, these parcels end up being parts of storm systems. This is how a lot of our moisture moves around, particularly onto the continents from oceanic basins and in the mid-latitudes too. So one of the things that we wanted to explore is whether a possible mechanism for this greater reliance on remote moisture is coming through the organization, sort of the intensification of storm systems that then pull in more moisture from the surroundings. And to give you a sense of what I mean by organized storm systems, here's one on the left. This I took when we were flying over, we were doing a campaign at South Korea, so an opportunity to capture a lot of mesoscale convective systems outside of the monsoon region. So you can see this system just towering above the clouds around it and also spreading out. So this is what we would call an organized system. And if you look at the literature, what we find out is that looking forward towards the end of century, this is end of century for a business as usual pathway, at least over the United States, this study is suggesting that we should see quite a few more of these storms. That's that green-blue shading here over most of the US, except for Texas and Florida. And the dots in this case indicate significance. So you can see the change in days with organized storms is the color bar scale. So what we've been doing at this point is trying to look for this signal in isotopic data that's captured at tower sites in the United States, and to see if we get the same signal, a drop in delta D for fixed Q, when large organized storm systems pass. And we certainly could have gone about an object analysis trying to identify MCS, these mesoscale convective systems, but we thought, let's just go with the biggest hammer we can find. And that in our case is going to be tropical storms or tropical cyclones. So I've had an amazing fourth year undergrad working with me, Julian Toogood, and he's been doing this part of the analysis, which he just presented at a NASA conference. He's been looking at a tower site in Alabama. It's a flux tower that happens to also capture water isotopic data. And so this is in the vapor, not in precipitation. This is part of the National Ecological Observatory, which we call NEON, and this particular tower is called the Tall site. And so Julian's been looking for changes in isotope ratios as these big storm systems pass through. So for example, I'm going to show you one case study, and then I'm going to show you a composite of all his analysis. So this one case, Hurricane Delta, that passed through the Tall site in October of 2020. Julian's plotted here precipitation amount, and you can see the hurricane passed through right around October 10th with this millimeters. And then here below is the delta D, the hydrogen isotope ratio and water vapor. And you see this very constant signal. And then as the storm comes, there's this sharp drop off. Now, to understand if this is a change in delta D for fixed Q, on the right, he's plotted delta D versus the log of specific humidity, or in this case, the mole ratio. So essentially, this is about twice the specific humidity. So what you see on the right-hand side is that there's that typical covariance, that first order thermodynamic connection between delta D and the log of Q, essentially a linear fit. And then as the storm passes, there's this sharp drop in the isotope ratio for fixed Q. And he's color-coded the points here too, so that you can actually follow from these pinks up top to these pink oranges down here. It's a near straight drop down on delta D with Q being pretty constant. So what if we look at all of these high Q, high specific humidity, low delta D periods at this particular site? So that would be these data points that fall in this lower right quadrant of this delta D versus log Q plot. And when Julian analyzed these data from NEON using then ERA moisture flux convergence, what he found is that when the NEON site, shown by the star here, experiences these very low delta D values at high humidity, there's this signal of very strong moisture flux convergence, pulling in moisture from remote places into the eastern seaboard of the United States. And so here's that same plot again. This is the NEON high Q, low delta D. I've circled the same area. The colors are a little different here, but this is the high moisture flux convergence region that I was just showing you. And now on the bottom, I'm also comparing that with precipitation amount, which you can see goes up in these places where the moisture convergence increases. If we now were to compare this with known dates where we know that storms have crossed through Alabama, where the NEON Tall Tower is, we see very similar patterns of increased moisture flux convergence on the eastern seaboard, and then also increased precipitation here on the bottom right. So overall, what this is telling us is that the signal that we see, that we expect to occur when we have this greater reliance on moisture convergence, moisture from remote places, this signal tends to appear when we have these larger, more organized storms. And so this seems to suggest a possible mechanism by which hydroclimate is shifting towards this reliance on more remote moisture. So to summarize that, we have isotope ratios as an indicator, something that's actually observable, that tells us about moisture transport through the dependence of transport on patterns of evaporation and precipitation. We see that there's this significant isotope drop or isotopic depletion at a fixed humidity value when there's greater convergence of remote moisture, and that's been backed by previous studies. We have observed this signal in tower data when large organized storms pass through. And the same signal appears as this long-term trend or this two-decadal trend in satellite observations, suggesting that many land areas are now seeing more of a dependence on remote moisture, ostensibly or possibly through this shifting in storm dynamics. So that's what I have. Thank you so much. Eager for any questions.